Hello, everyone, and welcome to Amplified, the podcast where we explore how artificial intelligence is transforming industries and amplifying human potential. I'm your host, Isha Majumdar, a high school student passionate about understanding how technology, science, and innovation come together to shape the future. Today, we are joined by Professor Somali Chaterji, who also goes by Sonata. She's an associate professor at Purdue University, a university faculty scholar, the principal investigator of the ICAN lab, and the founder and CEO of KeyByte. Her research explores how to make AI powerful, but also efficient, resilient, and useful in the real world. She works on-device machine learning for areas like streaming video, autonomous vehicles, and the Internet of Small Things, where small devices have to operate under real limits in memory, energy, and speed. Her work also connects AI to health, biology, agriculture, and human vitality. She is also a Frontiers of Engineering alum through the National Academy of Engineering. Professor Chatterjee, thank you so much for joining me today. It's a pleasure to have you on Amplify.
Yeah, I'm very excited. Everything is amplified around us, and I love the name as well. So let's get started.
Thank you so much. So, of course, let's start from the beginning. Can you tell us about your journey into a multidisciplinary space at the intersection of machine learning, systems, and use-inspired applications?
Yeah. So I think a lot of this journey unfolded very organically. So as a
Hmm.
professor, you kind of have to keep up with the time. So
Yeah.
this was good. Let's kind of go with the flow. So one of my first grants was an NIH grant. Do you know what that is?
Oh, yeah, I
NIH.
worked with NH. Yeah, yeah.
Okay, awesome. You are overqualified. You are an overqualified high schooler. So, National Institutes of Health, for those of
Yeah.
you who don't know. So, one of my first grants was a $3.7 million grant for MGRAS, which is
Hmm.
essentially for metagenomics data. You can think of it as a Google for metagenomics data. And it
Hmm.
was with, up north, Argonne National Lab. They hosted MGRAS. And my goal was to increase the throughput of this metagenomics slash genomics pipeline.
Hmm.
Now, throughput meaning, how much volume of the computation you're doing over time, right? Now, as I started working on it, initially it was kind of an engineering project. How do we
Yeah,
increase the throughput? Because there are lots of people from all over the globe
of
trying to,
course.
read and write to the different databases. They had Postgres SQL, which is an SQL database. We ported it to Cassandra,
Hmm.
getting a little bit technical here, which is a NoSQL database. We also tried Redis. So it was kind of engineering. And what happened is from this dry engineering project, we got lots of innovations. In fact, my company, KeyByte, came out of some of the exciting stuff. Never is just really about engineering, right? You give it
Hmm.
to these bright-eyed students, and I would like to think bright-eyed professors, and they meddle with it. I don't like the word tinkerer, right? They meddle with it, they have
Hmm.
innovation, and they come up with this cool idea. So what we found is when you have a database, right? A database has lots of nuts and bolts
Yeah,
underneath it, right?
yeah.
So you can tune the nuts and bolts of the database at real time when
Mhm.
it's basically digesting different kinds of workloads. Then you can keep up with the performance, even though the workloads are variable. So our
Okay.
goal was to increase the performance, which in this case was throughput, right? And then, this was in my assistant professor days. And then what happened is, all of this IoT, Internet of
Yeah,
Things,
internet. Yeah.
HPC. So I'm going to throw lots of acronyms, but for your audience, I'm hoping lots of high schoolers also get excited. So HPC meaning high performance
Yeah.
workload, right? So lots of different kinds of workloads. I started playing with those, and then what happened? These Internet of Things kind of got really exciting because Internet of Things basically are these sensors
Yeah.
that are deployed all around us, right? And I like the idea of ubiquitous computing. So this is when a lot of the centralized computing was also moving to the edge, right? So you have these sensors, but my goal was how can you make the sensors like not have them dumb, right? You don't want them just to sense, but you also want them to do some computation. So
Yeah.
I think that's when I started moving from can you approximate some of these large models on these sensors, right?
Okay.
And what happened is initially, these you can think about it as the sensing initially was maybe very simple, right? But with the advent of lots of different kinds of modalities of
Mhm.
sensing, you might have these multimodal algorithms that now have to be computed on these sensors, right?
Okay.
So with that, I'm going to move all the way to like things like foundation models and everything. So these days we are working with all the crazy models, the multimodal models, right? How can you have them compressed, approximated so that they can also work on these very resource constrained devices? And
Okay.
I really coined this term, which feels good, right? I coined this term,
Yeah.
IoST, meaning Internet of Small Things, right? So I think
Hmm.
if you look up IoST Chatterji or something, I would like to think my name will come up because I wanted to make sure that we emphasize that smallness, right?
Hmm.
And that does two things. One is you are approximating the algorithms, but at the same time, you want to make sure the algorithms are giving you outputs that are the kinds of outputs you want. What
Yeah.
do I mean by that? Meaning, if you want a timely output, right? So,
Mhm.
say it's a self driving car, right?
Yeah.
So, you have a small mobile GPU, graphics processing unit on the self driving car, which is doing real time object detection, etc. Right?
Hmm.
So, although you're compressing a very powerful algorithm on this mobile GPU, you still wanted to give you timely answers, right?
Yeah.
So you don't want it to, or you also wanted to give you accurate answers, right? So
Hmm.
there was this Pareto frontier between accuracy and latency, right?
Yeah.
So that's how, like we started working with Internet of Things data. And then I'm like, oh my gosh, look at all these little computers that you
Hmm.
don't just want to use as sensing agents, but you also want to do computation on them. So
Hmm.
adaptive computation on these little devices. So that's kind of like the story of how I moved from metagenomics all the way to all these multimodal sensing data. And I kind of like the idea now that I think back, right? It's insightful because I like the idea of metagenomics in
Hmm.
a way because I like vitality, I like fitness. So if you can have, this microbiome, metagenomics is basically the genomics of the microbiome.
Yeah.
It comes from community genomics. And for a computer scientist, that's actually mind boggling because it's not just the genome of one organism, it's the community genomics, right? That's what
Mhm.
people, my friends, folk, my Anant Krama here, we worked on this cool community microbial genomics instead of having the genomics of a single organism. From there, I moved all the way to, you have the sensing, the always on sensing, right? You have these small sensors,
Mhm.
but we don't just want them to sense. We also
Yeah.
want them to compute and
Yeah.
compute adaptively so that, these big algorithms can give you the right answers on these small resource constrained
Mhm.
devices.
Absolutely, absolutely. And I want to go back to what you said about cars, is because you have to get it accurately and fast. Because of course, one, if you get inaccurate results, you could crash the car. And of course, when you're driving, this is real time. You're making decisions real time. And I want to attach this to a broader question. What role do systems and infrastructure play in scaling AI? So maybe going from an Apple Watch to something as big as a car, where real people's lives are at stake.
Yeah, that is an excellent question. So, systems and infrastructure in scaling AI is a very important question, especially because AI is like all pervading. I
Mhm.
think like these days, starting from the students to the execs, everyone is eating, sleeping, everything AI, right?
Yeah.
And AI is really all over the place, right? So
Yeah.
you want to make sure you're mindful of the kinds of infrastructure that your AI is ingesting. And people sometimes think, maybe your infrastructure is infinite, right? That is not really the case. And that's how I really like thinking of, we're doing a lot of work on ODML,
Okay.
um,
ODML.
which is on device machine learning,
Okay.
right?
Oh,
Uh,
yeah, of course. Yeah.
yeah. So there are like two aspects to it. So one is, you should not think of infrastructure as being infinite, right?
Mhm.
Because I think we have a societal obligation that if you think of infrastructure to be infinite, I'm sure you've heard about the data centers,
Mhm.
coming up all over the place and how these utility costs are increasing and people are resisting to all of this, right? But at the same time, people want to use, many of the people, they want to use all the AI, the ways in which AI is making things easier, right?
Mhm.
I would say for the more thinking kind of jobs, right?
Yeah.
And even like even in the factory, right? You can look up something and maybe use LLMs and to give you answers to stuff really fast, right? So it is convenient, but at the same time, it is important to remember that a lot of these data centers are powering these algorithms. So I would like to think of it in two ways. One is the data centers, right? The data center costs. So these days, like I said, you want a lot of the computation to happen on the sensors, right?
Yeah.
And I like using the term right sizing or on device ML, right? So the aspect there is it's kind of helping because you are doing the computation on the edge, right? The edge intelligence, the on device intelligence, right? The other aspect which kind of powered my company called KeyByte,
Mhm.
one aspect of it, right, is the data centers are largely over provisioned. So they
Mhm.
over provision, and there's a reason for that, right? Because you have to meet all the customers, and you have these spikes in usage, right?
Yeah.
I don't want to give you the exact number because, but I would say like 40% of it is actually utilized at any
Okay.
point. You might find some conflicting numbers there, but it's pretty low, the utilization. And they have this over provisioning because you can have the spikes in usage, right? So
Yeah.
that over provisioning is problematic, right? Because data centers cost money, they cost
Yeah. Of
water,
course.
they cost
Yeah.
all the different physical stuff that has to keep the data center alive, right? And of course the footprint of data centers is also increasing because of all the AI, right? So that is one aspect. The other aspect is, I think I like the work that I do, ODML, that because right sizing computation, I think it should be a design choice that you should not be using more compute than you need to,
Mhm.
especially if you think of all the foundation models and frontier models, right? So just for terminology, I think I'll have a lot of you have a lot of young viewers, right? So these frontier models, I like to think of them as these very powerful oracle models, right?
Mhm.
So frontier models are the highest class models, right, that have been trained on lots and lots of data,
Yeah.
right? So frontier models are foundation models, but not all foundation models are frontier models, right?
Mhm.
So one of the ways in which you can tame some of this cost is if you look up the numbers, right? The amount of data, the amount of tokens on which these frontier models are tamed is huge, right?
Mhm.
So if you can amortize the cost of that training by using these frontier models or foundation models in lots of downstream uses, and I actually use this in my keynote in the high school hackathon here, and I'm going to use that here as well because I think it's useful. So a lot of the times, what you do is these foundation models, when you have these downstream applications, right? You
Yeah.
want to amortize the cost by using them for lots of downstream applications, right?
Mhm.
So you've trained it once. These are these very smart Oracle models that know it all, right?
Yeah.
And then you fine tune the models for various downstream applications,
Mhm.
right? That is one aspect. But the other aspect, which I think is kind of more relevant to what I do in my lab, but God knows, right? I keep innovating. I'm curious. I keep changing my trajectory some, which makes it really exciting. So you also don't want to be doing over serving, right? So when you have these frontier models, when you're doing inference using these models, you don't want to be over serving, right? So we approximate them when you're doing the inference as well. So one is amortizing the cost of training of these frontier models, right, on lots and lots of data by fine tuning them for various end using or prompting them for various end users, right?
Mhm.
So making the most of that training, right? But the second is when you're doing the inferencing or the serving, you want to make sure you're right sizing that serving. Right. So the key thing here is like we should not think of infrastructure as being infinite, especially as all of this AI is all around us. I think there is that societal footprint, right? The huge amount of data center costs and all of that people are starting to realize in their
Mhm. Of
utility
course. Yeah.
bills. There has been some thought that if you have of course the US electric grid, I think like for 15 years there hasn't been much update. So that is a problem. So some of these companies go back and tell these electric grid people that, hey, you really need to update your electric grid. So maybe it's going to be a win-win where the electric grid is going to
Yeah.
be updated and things will work well because of the efficiencies of scale, right?
Mhm.
But nothing is infinite, right? So we should be very mindful of the footprint that all of this AI is costing the world, right?
Yeah, yeah,
Yeah.
absolutely. I think with the advent of AI, it's been a both, a huge positive and a huge negative in a lot of ways, and kind of balancing that is an issue because, of course, you have the AI depletion, water depletion issues, a lot of that, electric grid and all these training the models on these huge data sets that some people worry about privacy even. But what are some maybe of the real world positive or real world applications of AI in areas like healthcare, agriculture, human health, fitness, and vitality.
Yeah, that is very near and dear to my heart. But before we move on to that question, one another key point, and I kind of want to make it because
Yeah.
I think this is kind of key to our community here as well. So, SK Hynix, for example, is a company that makes memory chips, right?
Mhm.
So, one thing that I kind of want to share with our audience is that when you think of efficiency, right, one of the things that we don't always think of, doesn't happen very intuitively in our heads, is there are two kinds of efficiency, right? So, you can think of like compute efficiency
Mhm.
and there is memory efficiency, right?
Okay.
So I'm actually going back to our previous question, and then I'll come back to your current question because I think I would not like it if I left this memory thing out. So a
Yeah.
lot of this computation is memory bound. So what do I mean by memory bound? Meaning memory is the bottleneck, right?
Yeah.
And I kind of like the way I explained it in the hackathon, and this is fresh from this weekend, so I'm going to explain it just the way I explained it to my high schoolers and middle schoolers, right? So you can think of the compute in flops, right?
Yeah.
Floating point operations per
Yeah.
second. And the memory is, you can think of it, it's not just the amount of memory, but it's also about the movement, right?
Mhm.
So you want to make sure that, there is a lot of technical stuff here with the KV cache and all of that, which may be a little bit too complex for our regular audience. But you want to be making sure that you're mindful of the fact that a lot of the times you want to bring in this memory efficiency, right? Not just the compute efficiency, because a lot, you can think of, this is the analogy. Let's get back to the analogy. So if you think of like a chef who's cooking, right? And you're cutting vegetables and all of that, that's your compute, right? But maybe you have the sous chef who's getting all the stuff for you, right?
Mhm.
So that data movement is oftentimes the bottleneck, right?
Mm.
And the reason I mentioned this is because, I was talking to a Googler and she was telling me, memory is a big thing, right? These memory chips are so expensive and
Mhm.
they have not kept up with the compute chips. And that's how the companies like SK Hynix, etc., they are really worried about being able to continue to produce the memory chips that are required by all of these memory bound operations, right?
Yeah.
So I wanted to make sure that we give some idea of this memory efficiency and what is memory bound, right? Having said that, let's go back to your question, right? This is how greedy I am. I want to give it all to our audience, right? Now, our question of, I gave you a little bit of the gloom doom, right? But what are we doing? Right? What are we doing with all of these really cool algorithms, right? That is what excites my lab. My lab is called ICAN, Innovatory for Cells and Neural Machines. And I think that blends very well with my personality. And I would like to think the personality of my collaborators, my students. So it has been a great journey, right? And that ICAN is a very positive mindset. So what is the positive changes that, all of this AI is doing to the world around us? So I like saying that my lab is use-inspired machine learning, right? So we're not just building all these machine learning algorithms in isolation, but we're thinking of what are the possible use cases, right? And that has really helped me. Of course, you have to pay the bills of your research, right? So we get funding from a lot of different agencies, and I think that helps as well because different funding agencies bring forth, different ways of thinking of these problems. For example, our lab is funded by National Institutes of Health,
Mhm.
by National Science Foundation, by USDA, which is the agriculture funding agency, USDA NIFA, by DoD, Department of Defense, right? And then we also have a lot of private sector funding from various industry
Mhm.
like Adobe, just recently got NVIDIA, etc.
Okay.
So the reason I tell you this, I think wearing these multiple hats of use-inspired ML is very helpful. So let me give you an example of how our algorithms are helpful in ag, for example, in digital ag, for example, right? So one of the things that I want our young audience, maybe all audience of all ages, right, to know that labeling data is very important, right? So when you're doing supervised learning, you want to have labeled data, right? So for
Mhm.
example, if you think of like a farm, right, and if you think of like crop diseases, right,
Yeah.
so there is a specific kind of disease that is as a result of, say, discoloration in leaves, right? So based on how much discoloration there is, say you label that, okay, this is grade 1 disease of this
Mhm.
type, grade 2, and so on, right?
Yeah.
So you put those labels, right? And then you tell the model to predict, hey, how severe is this disease, or what is the disease, depending on what your question is, right? Now sometimes what happens is, especially in newer scenarios, right, if you
Mhm.
have newer diseases or a new domain,
Of
this
course.
label data is hard to find, right?
Mhm.
One of the things that we are doing using these foundation models is, can you use these foundation models even when your labeled data is very scarce, right?
Mhm.
I think this is a very practical problem. And now we've moved on to very low levels of these label data. And we see that because of the kind of strategies that we have used, we shine even brighter. You have to do this benchmarking, right? So when we do these benchmarking against our competitors, right, then we see that we shine even brighter when you have very low labeled data, right, which is very helpful, right?
Yeah.
So these are some of the practical problems that we think about. One is right sizing, right?
Mhm.
The accuracy, latency, Pareto frontier. The
Yeah.
other is you want good enough results, right? You may not want, say, if it is like captioning, right? If you have some error in captioning, it would still be fine, right?
Mhm.
Whereas if you're like, it's a self-driving car, right? You don't want too much error in the detection, etc., right? Maybe some centimeter error is fine, but it varies on the, based on the application, right?
Yeah. Of
So
course.
one is that right sizing based on the application, that you don't need the best model, right? You can run a lesser model for
Mhm.
a application that does not need as much accuracy, right? And the other is, can you also work with lesser levels of these labeled data, which, so these are the kinds of very practical use cases we try to work with.
Mhm.
And the other thing that we do is we want to make sure all our code, etc., which is, I think, something that we're trying to do increasingly well. And I think with all of this Claude code and everything, it should be easier. The code should be something that people can use and work with. Right.
Yeah.
So that is something that we've been very mindful of even before the age of all of this Claude code and everything,
Mhm.
right? Where it was all handwritten code, right? Handwritten grad student code, right? So we would like to think we are trying to attack these problems that are very real problems, less labeled data. How do you work with, memory efficiency, energy efficiency, right? That
Mhm.
is the other thing, right? So if
Energy.
you have a drone that is scouting these fields, right? And say
Mhm.
you need it to be charged every 20 minutes, if you can be more efficient with, kind of trying to scout fields and maybe early detection of disease, that would be a good thing. So a lot of our work is driven by energy aware computing, latency aware computing on the one hand, and then how do you work with less levels or lower levels of label data, so you can, maybe even do zero shot, right? So things like that.
Okay. Okay. And of course, there's so many issues with like resource limited devices, like the drone with such a small battery, or such small labeling data, of course, with new diseases. But I was wondering if you could explain more on why is it hard to deploy AI on small or resource limited devices, and what does on-device machine learning do to help this?
Yeah. So, so there are many facets of this on-device machine learning, right? So I told you, if you think of, without trying to get too technical, right? So you have, if you think of these LLM models, the various vision language models that we are working on, right? So you have this pre-filling stage, right? When you're just kind of understanding the query, right? And then you have the decoding stage. So getting a little bit geeky here, right? People can look this up. The pre-filling stage is generally compute limited, compute
Yeah.
bound, and the decoding stage is generally memory bound, right? So
Mhm.
this is one aspect. The other aspect is, like I said, you don't want to be over serving, right? So
Mm.
if you can work with a lesser variant of a foundation model, um, one is you want to reuse that training, right, by using it for multiple downstream use cases. But when you're working on these smaller devices, you may not want to use the full blast model, right? You might want to use a lesser variant of the model. The other thing that we do is we also do this at runtime. So at runtime, can you pick the best model for your specific use case? And
Mhm.
this use case can be determined by multiple things. So this is something that, I recently gave a talk, and I talked about our work on Agile 3D. And Agile 3D, for example, does 3D LiDAR based object detection.
Hmm.
right? And this is, you can think of that Waymo with this LiDAR sensor on top, right? And it's doing real-time object detection.
Yeah.
This was published last year in a conference called MobiSys. It's a mobile systems conference. And what you have to do is, you can think of two things here, right? And this is basically taken from our paper. One is content, right? So if you think of a scene, right? If the scene has a lot of pedestrians, a lot of bicyclists, versus if you have a scene with lots of highway trucks, right? So that those trucks may not need as much precision, right, in detecting those bounding boxes because it's
Mhm.
easier, right?
Yeah.
They're larger. Whereas you have if you have these humans, these pedestrians, right, you might need more sophisticated models. So
Mhm.
what we did is at runtime, we are able to pick a more sophisticated model or a less sophisticated model based on the content,
Okay.
right? So
Yeah.
that is one aspect. The other aspect, especially for these resource constrained models, is sometimes that isolation is not great on these resource constrained models, right? So if
Mhm.
you have multiple applications running at the same time, right, it gets even harder, even more resource constrained. And what happens as a result of that? So if you have, we call this SLO, latency SLO. So if you have a latency target that you have to meet,
Yeah.
because this is real time, it may be pretty low, right? I think for if you think of LiDAR, it's generally 50 to 100 millisecond per LiDAR frame. Right
Mhm.
now, if you have to maintain that latency target, you'll see like if you have a lot of contention, generally the variance in that latency becomes pretty high. So it can basically have these surges, which is going to be really bad for real
Yeah.
time, right? So you have SLO misses, right? So these are some considerations when you have these really resource constrained devices. I would say you want to do this, you don't want to be doing over serving of the models.
Yeah.
You want to pick the right variant of the model for the task at hand, right? And
Mhm.
then you also want to make sure don't have too many SLO misses, right? And then you also want to consider the memory efficiency, right?
Mhm.
Because that is a big thing. So you don't want unnecessary data movement, because that unnecessary data movement can, unnecessarily cause energy loss, right? So you have to be energy aware as well. In a lot of these cases, if you think of battery powered
Yeah.
uh, devices, right? So all of these, I think, energy aware, memory aware, which is sometimes not obvious to people. How do you
Mhm.
improve the memory efficiency, right? And then also contention aware, because you might have multiple things running at the same time on many of these devices,
Mhm.
right? So all of these, I would say, are considerations for ODML. Another thing that people don't typically think about, they might think of right sizing, but the other thing is robustness, right? So if
Mhm.
you basically have suddenly you're running too many applications for whatever reason, right? Your model performance may degrade, right? So you kind of want graceful degradation. So there is also the aspect of resilience on these small devices, right? So we are expecting a lot out of these small devices. I think all of these considerations come into play for ODML,
Mhm.
on device machine learning.
Absolutely, absolutely, and of course, how you accommodate depends on what your task is, versus truck versus human and that kind of thing. But generally, going before the models, your work itself covers so many areas, like video analytics, smart sensing, and health-related applications. What ties these problems together, and why does it matter to run AI close to the data in settings like, of course, the self-driving cars and IoT devices?
Yeah. So I think this edge intelligence, for various reasons. So, for example, if you think of like healthcare data, right?
Mhm.
There, I think it might be more to do with privacy, right? But in general, if you have to move everything to the cloud, there is that latency,
Mhm.
of course.
Of course, yeah, like you
You're also
spoke
paying the
earlier.
cost, right? Moving data, data is not as private, right? If you have
Mhm.
to continuously shuttle between the cloud and the device. But we recently also got a paper. It's called a Prospect. It's going to be
Mhm.
presented in May in Saint-Malo, France. It's going to appear in Census, which is a top sensor networks conference. And so what we do in that is, if you have a transformer, for example, right? How
Mhm.
do you cut that transformer, right? And how much do you offload, and when do you offload, right? So
Mhm.
remember, we talked about various funding agencies. This is something that DoD is very interested in, right? So if
Yeah.
you have the opportunistic ability to adaptively offload from your lesser device to your more powerful device,
Mhm.
how can you do that? And what happens
Mhm.
is then you can get more accuracy,
Okay.
right? because your Pareto
Mm.
frontier kind of elevates, right? Um, so yeah, there are various considerations. So it's not just on device ML, right? You can
Mm.
offload adaptively as well. And the considerations for this on device can be slightly different. For example, if you consider healthcare data, it might be more to do with privacy, right? But in general, just reducing the need to move data to the cloud and again, get back the result of the computation from the cloud, it sounds very inefficient, right? Even if you consider the self-driving case, right? We have an NSF center, it's called Chorus, right? So you have, you don't want to constantly offload the computation and do the computation on the cloud and get it back, right? Sounds almost like futile in such a use case, right? So I think increasingly a lot of the use cases are you do the computation where you're getting the data. Data is closer and closer to where it's being generated, which kind of I think from the efficiency standpoint is also very helpful.
Okay, okay. That makes a lot of sense. And it's very interesting to see how, even like many different organizations are interested, like you said, the DoD, and how this can apply to so many different fields. And I want to start closing up, but before that, I have a couple more questions to ask, specifically for students, right? Like you were talking about how, back in the day, a lot of grad students would be writing the code, but now Claude Code is writing it. So as tools like, Claude Code and other agentic AI systems become more common, how do you think they'll shape the future of computer science and interdisciplinary work? And what advice would you give to students who want to prepare for that future?
Yeah. Uh, I'm still scratching my head, right? Because this is so new, right?
Yeah.
All of these agentic AI pipelines, Claude Code, all of this, right? The companies have started rolling it out, right?
Mhm.
And I was talking to people in companies, students, colleagues, Amazon, and all of these big tech. They're rolling out, you have lots of tokens, just go and be this 10x programmer, right?
Mhm.
Using all the tokens, right? But I think at some point this has also come up, like, if you're over ingesting all of these tokens and you're generating a lot of not great code, right?
Yeah.
You're not really getting the bang for the buck. So at some point it might be, oh my gosh, are we really being able to get enough out of that token, or we have sloppy code, right? So that is one aspect. Right now I think they're getting infinite tokens to generate to become this 10x programmer, right?
Mhm.
But I think having the insight, I would say you still need to kind of learn to code, right? And
Of
maybe
course.
like 1 year down the way and the pace at which a lot of this is moving, things may change. But as of now, this is my insight, that you still need to be creative. You need to ask the right questions. You need to code with AI, right? But
Mhm.
if you're coding with AI, you kind of have to have that insight, how to code, how to see sloppiness, or how to see
Mhm.
things that have not aligned with the query, right? How to do the prompt injection,
Yeah.
right? Doing this coding in tandem with the agent, right? And being able to see what is not in alignment with what you wanted the agent to do, right? And then also, I think this is something that I was thinking, and maybe this is going to change with the as the ecosystem rolls out, right? These test cases, these test routines, right? So if you have these really corner cases, right? Can you generate those test routines, right? How effectively, because typically the person who writes the code does not generate the test routines, right,
Mhm.
in the real world, right?
Yeah.
How is that going to look like when you have these agentic pipelines, as you increasingly adhere to it, if there is a little bit of sloppy code in these production pipelines, that may result in lots of detrimental effects that we've also started seeing some of that. So that is one, test cases. The other thing is the privacy, the cybersecurity, right? If you
Mhm.
want the pipelines, the agentic AI to do this, or the Claude Code or whatever, you wanted to do more, you give it more privileges, right? So there was a talk in a recent symposium by the CTO of Scale AI, and she was talking about, contextual privileges, right? But how
Mhm.
do you know, right? The more privileges you give, the more the AI can do, right?
Yeah, of
And
course.
at some point, if Cloud Code, for example, wants to write a bash script and get additional privileges, right? What's stopping it from doing that, right?
Yeah.
So can you create these guardrails so that, you don't have these mistakes and many of these uh, codes that are running in production, right? And if you think of like cyber physical, right, where many of these are actually doing things in the physical space, right, that could result in really bad
Mhm.
effects, right? So I would say being able to test code, being able to actually get that coding insight, right, so you can see, run test cases, design test cases, making sure you have those contextual privileges so that the AI is not all over your system, right?
Mhm.
I think there are also privacy ramifications, right? Because the more the privileges, what is it going to do?
Yeah.
So and on the other side, I think the more holistic side, this is so new that I was jotting that points. Like, you have to develop the intuition, right? Unless
Mhm.
you've done coding yourself, will you develop the right intuition, right?
Yeah.
If you're blindly, I think I don't really like the word vibe coding, which is the more non-technical word, right? So if you're blindly coding, right, you you'll possibly generate sloppy code, right?
Yeah, of course.
And you will not detect those problems. And these are like real world use cases, right? So that becomes very important to make sure that you're generating good code. You're aware of these cybersecurity implications. You're aware of the various privacy implications,
Mhm.
how much privileges to give to your coding agent, right? So I think in general, just having the intuition to code, being all world in some way, so you know how to detect various problems. And I think creativity is the other thing, right?
Mhm.
So I think there is this might sound a little bit old fashioned, but I think the struggle to learn, right, where you're kind of scratching your head and trying to code better, right? I think those intuitions that you get, I don't want that to get lost, right?
Absolutely.
So
Yeah.
coding is still kind of that art of coding,
Yeah.
right? So I don't know, maybe down the line this will get very mechanized, right?
Mhm.
So I think while this is still evolving, learning how to code with the agent, right?
Mhm.
But being smart on the human side as well, and knowing what the agent is actually giving you, being able to
Absolutely.
recognize that. All of that is important. And it's important to be very creative as well,
Mhm.
right? And one other thing, which I think you listen to all these godfathers of AI, right? Hinton, when he did deep learning, right, it wasn't really cool then, right?
Mhm.
But look at how
Yeah.
things change, right? When the context changed, when you have lots of GPUs, lots of data, right?
Mhm.
So don't always jump onto the cool bandwagon, right? Do some of the classical computer science, right? Learn some of the insights into various
Mhm.
algorithms, right? How do you do better search, right? Simple things that are underlying a lot of these, sort of like the chat gpt, the gen ai kind of bandwagon, right? So learn some of the more classical things and get into the foundations, the math, right? And maybe even the physics, right? Because there is going to be increasing interaction with this physical ai, right? So understanding the broader ecosystem, and read and be curious, right? Because I think the way at which the scale of innovation, I was reading, there is this company, by two people, and I was looking up this company. It's this billion-dollar company. It's called Medbee. It's a
Maybe.
health company, telehealth company, right?
Mhm.
And it's just run. It got started by one person. It's not an AI company, but everything is done by AI, right?
Okay.
So, like Sam Altman also said, you can have these, billion-dollar companies by couple people, right? So you can do a lot, right? So
Mhm.
developing that insight, developing that creativity, knowing how to work with AI. And if you're developing these companies and these great ideas, right, I think there is that responsible AI, right? You want to make sure you don't have this AI agent go out totally off its guardrails, right?
Yeah.
I think all of these, while you have great power, but that comes great responsibility.
Yeah.
And so being able to have that rigor in the design, developing that intuition, I think that is important. And the other thing is, I think just the struggle of coding, that should
Mhm.
not be lost. That art
Learning
of,
is in the friction. Yeah.
yeah, learning is in the friction. I love it. The calluses of transformation, right?
Mhm.
Learning is in the friction. I think that is very important. So you should be waiting. You should be struggling a little, because I'm a little bit concerned if this generation knows how to struggle, right? Yeah, sounds a little bit pessimistic, but I also like the fact, this is crazy. The latest thing I learned is there is this Meta took over this app, and what is it called? You might know this. It's the social network for chatbots. Meta just took it
Oh,
over.
yeah, I've heard of this. Yeah, yeah,
Yeah,
yeah.
it is crazy, right?
Yeah.
Like social network for chatbots, right? Where is the world going? So
Yeah.
you have to go with the times, right?
Mhm.
So you can do all of these cool things. So that creativity, right? And I really like Dr. Seuss. This I really like. Think left, think right, and think low and think high, or the things you can think up if you only try, right? So you have to struggle, you have to try, you have to be creative, right?
Mhm.
And you have to build up your foundations of math, because a lot of this is math, right? The compute, right?
Mhm.
So I think that is very important. Classical education is always important. There are no
Absolutely.
quick cheat
Yeah.
sheets,
I
right?
remember, like, I think for me and a lot of other students, before AI was a big thing, the thing you learned most from was when there was like one small syntax error in your code and you had to look through the entire thing. So I think you should really know your code inside and out. But you can still, of
Yeah.
course, use the help of LLMs and these, new tools. But this conversation was incredibly insightful, and thank you so much for sharing your perspectives and your experiences, of course, and your wide array of experiences. And I especially love how you highlighted the interdisciplinary. Sorry, the interdisciplinary. I can't pronounce it, but you know what I mean.
Interdisciplinary. Yeah.
Of thinking,
It's good. The struggle is good, right?
yeah, of thinking about the applications of this and like the way each thing interacts. Is there anything you want to say before we end our conversation?
No, I think I've been creative in my research. It's been very organic. I
Mhm.
love working with people. I think something that struck me is in this company, like there is a social aspect to everything. So in this MedBee company, the
Yeah.
founder was saying, I just have my brother, but I actually want more people because I'm lonely, right? So going to college, interacting, having the college experience, like, talking to people, right? Doing this podcast, this experience, right? I am very passionate about it. I am in the right profession, right? Like
Mhm.
I want to learn myself. And I think spreading that flame to learn more, right? I
Mhm.
think you need to teach, or I need to teach my students how to love to learn more, right?
Of course.
It is lifelong learning, right? And also you kind of have to be agile, right?
Mhm.
If you're like, oh my gosh, no cloud code, nothing, just keep coding on your own, right? You have to move with the times, right?
Yeah.
And the good thing about an academic profession, or even working with industry, I work a lot with industry, it's the best of both worlds, right?
Mhm.
You have to go with the times.
Mhm.
And I think also being able to instill that love for learning, right?
Mhm.
uh, Being passionate about it, right? Struggling to make sure you make your dreams meet. And I think something that I'm trying to do is, I'm not great at it, but maybe what do I want to do this week? What do I want to do this month? Right? The short term goals, but
Mhm.
what is my vision, right? And
Yeah.
sort of keeping some agility in it, right?
Mhm.
I'm not stuck to it, but
Mhm.
at least I have these goals, right? That
Yeah.
is one. And the other is, what do you want to do to fuel some of this, right? For example, I love to run, right?
Mhm.
I don't run as fast as cross country runners, but I do like racing people,
Yeah.
right? So having these additional avenues to keep that flame burning, to fuel your love for learning, you need all of this activity. So I think I'm also very passionate about fitness, about activity, right? So that's how I like the idea of all the wearable computing, right?
Mhm.
Like, can you make sure that that preventative, right? The
Mhm.
vitality, so I think that microbiome, starting with that, right? I think it's esoteric. So I think some of that, I feel like you should be passionate about what you're working on. And that has increasingly, like, deadline driven, right? I as a person am also deadline driven. So I think there is that fuzzy boundary between my personal life and my research life. And I don't have clear cut boundaries, which is just my personality, right?
Mhm.
Be you. If you don't like it, adapt to what you like, right? Because
Absolutely.
I want to have my life's journey to be a journey that is enthusing me to go faster, right?
Mhm.
So I think that is very important to kind of write it down and to see if that's actually igniting you to go faster, right?
Mhm. Absolutely. And thank you again, Professor, for this conversation. And to everyone listening, thank you so much for tuning in to Amplified. If you enjoyed this episode, be sure to share it with your friends and stay tuned for more conversations on how AI is shaping the future. If you yourself want to be a podcast or you know someone who does, reach out to me at ishamajumdar@gmail.com or for any general questions as well. Until next time, keep learning, stay curious, and keep exploring how technology can amplify human potential. Thank you so much.
Awesome.